In this video, we're going to take a look at the fundamental theorem of calculus, this time focusing on part 2, or what I'm going to call the derivative part of the fundamental theorem. And before we start with that, we have to define one key term, and that is the idea of an accumulation function. And another name for an accumulation function is an integral defined function. And this type of function has an input that determines the boundaries for a definite integral for a given curve. And notationally, what this looks like, let's define a function g of x to be the integral from a to x, where a is going to be a constant value for some function f. Now, defining an accumulation function, we only want this x, this input, to determine the boundary on our definite integral. But what we don't want is for that input to change the inside function f. So what we're going to call this is f of t, and say we're evaluating the integral with respect to t. And in this case, t is just a dummy variable, or a placeholder variable. And this could have been any variable except for x. The key thing is, x cannot get to that inside function f. It must only determine a boundary on the integral. Looking at a graph of the curve f, what we're evaluating is the integral, or the area, from a constant boundary a to some variable end boundary x. So we could stop that here, or we can move x farther along and create a new area. And the idea is we can move x anywhere, even to the left of a if we wanted to. But what is the purpose of an accumulation function? As implied in the name and shown in the visual to the left, accumulation functions allow us to accumulate area. And in real-world terms, other concepts we associate with the idea of accumulation are things like precipitation, distance when we think about motion, and even money. And what these have in common is that all of these things can be modeled with continuous functions, which makes the process of integration possible. Now, these real-world concepts will not be the focus of the remainder of this lesson. What we're going to focus on instead is, what is the derivative of an integral defined function? A question that might not seem interesting at first, but has big implications moving forward in our understanding of both integrals and derivatives. And so now we'll move into a basic proof for the big concept in this lesson. And to start, let f, or big F, be the antiderivative of the continuous curve, or continuous function, little f. We will then define g of x to be the accumulation function, or the integral from a to x, for f of t with respect to t. Recalling that if we want x to determine the end boundary on this integral, we must use a replacement variable for the function inside of the integral. We will then carry out the integral operation and rewrite this as the antiderivative of little f of t, which was big F of t, evaluated from a to x, which then allows us to utilize the first part of the fundamental theorem of calculus, which states that any definite integral is the antiderivative at the end boundary minus the antiderivative at the starting boundary. And what we've done is change this from a function that would have been very difficult to differentiate to one that will be very easy to differentiate. G prime of x will equal the derivative of big F of x, which is little f of x, minus the derivative with respect to x for big F of a. And the reason why I isolate that term is because I want to show that this term is going to equal 0. A was a constant in the original problem, so big F of a will also be a constant, and the derivative of any constant will equal 0. And we can conclude that g prime of x just equals the function f evaluated at x. And notice, it almost appears that from our original g of x function, when we differentiated it, x simply took the place of that dummy variable t on our inside function. And that gets us to the main idea, which is the fundamental theorem of calculus, part 2, which essentially states that if a function defines the area under a curve, or under a continuous curve, to be more exact, then the derivative of this accumulation function is the curve itself. Put another way, since derivatives describe rates of change, the rate of change for an area under a curve, or the rate of change for an accumulation function, is entirely determined by the curve itself. And the biggest takeaway from this is that this proves that the derivative and the integral are inverse operations. Differentiating an integral defined function eliminates the integral and leaves you with the function inside, a connection that bridges the gap between differential calculus, the study of derivatives, and integral calculus, the study of integrals. Now, the consequences for the second part of the fundamental theorem. As I mentioned, we're not going to focus too much on application, but rather the mechanics of differentiating accumulation functions. So in general, let's define an accumulation function, a of x, to be the integral from one function of x, g of x, to a second function of x, h of x, accumulating area under the continuous curve f. What I want to get across in this process, when we define an accumulation function, the integral is really an outside function on this problem, and the boundaries are the inside functions of x. And all of this is to say that when we differentiate an accumulation function, we must consider chain rule on this derivative. So now to differentiate this function and get a prime of x, the derivative eliminates the integral, and our top boundary, h of x, takes the place of our dummy variable t. But chain rule states that we also have to multiply by the derivative of that inside function of x. We will then subtract the lower boundary taking the place of t, so f of g of x, times the derivative of that inside function, g prime of x. And notice that this derivative still has the same basic frame as the first part of the fundamental theorem of calculus. We can see that we've really differentiated what we called big F of b minus big F of a. And one thing to note from this that's related to the earlier proof that we saw for the second part of the fundamental theorem is that if either boundary is constant, the derivative will equal 0 for that part. And so we'll end with a couple of examples to show off the mechanics of this process. The first example, let's write the accumulation function f of x equals the integral from 0 to x of 5t with respect to t. Evaluating f prime of x, the integral will be eliminated, and the top boundary x will take the place of t. So we'll get 5 times x times the derivative of x, which is 1, minus the bottom boundary taking the place of t, so 5 times 0, times the derivative of that boundary, which is also 0. And this will all simplify down to state that f prime of x equals 5x. And in this one, it more or less looks like x took the place of t, as we saw in the earlier proof. And for the second and final example, let's write the accumulation function g of x equals the integral from 1 to x squared of the function 4t minus 1 with respect to t. Differentiating will eliminate the integral, and the top boundary will first take the place of t. So we'll get 4x squared minus 1 times the derivative of that inside function x squared, which is 2x, minus the bottom boundary 1 taking the place of t, so 4 times 1 minus 1, times the derivative of that boundary, which is 0. And this will simplify to give us that g prime of x equals 2x times the quantity 4x squared minus 1. So the mechanics on these problems are a little bit strange at first, and they do distract from the true purpose and application of accumulation functions, which will come later. For now, do your best to understand what is going on here mathematically, and just make sure to practice it enough until you feel comfortable. That's all for this lesson. Thank you for watching.